Hi, I'm Alan Bowling in the Department of Mechanical and Aerospace Engineering at the University of Texas at Arlington. This presentation is a two-part series about systems of equations and matrices in engineering. So let's get started. In an earlier presentation, we looked at this problem of moving from this point to this point. And we were going to examine the distances involved in moving between them. So we looked at the distance involved in moving over the street, and we also looked at this other distance where we move as the crow flies, where you just go straight over all these buildings and go straight from one point to the other. Well, in this presentation, we want to look at a little bit different problem where we also have a friend who's starting at this point, and our friend is trying to go to this point, but our friend is also trying to move as the crow flies, and they're going to fly over all these buildings and go straight there over all these buildings. But what you notice is that if we're doing this at the same time, there's a chance that we're going to collide right here in the middle. That's possible. So we want to figure out where that point is where we might collide. So we can do that by translating this problem into the math world. So let's do that. Okay, so again, when we go to the math world, we simplify. So we get rid of all the extraneous information, and we just look at what we need, which is these are our destination and our origination points. So we wanted to move to C. But this time we're not going to use 2D vectors. We're going to develop a set of equations to describe those movements from A to B and from D to C. So what we're going to do is set up something called an axis. And again, we're going to assume all these streets are straight, perfectly straight. So we're going to set up an axis, and we're going to call this axis, we're going to call this the y-axis. Now if you remember from previously, this was east, and if you measure from here that way, you were going in the y. And we set up this other axis that goes like this direction. And if you remember previously, this was what we called north. And if you measure from here onward up, that distance was x. So if we set up this grid, we're going to give these points some values. So point A here is going to be our starting point. So we're going to call this 0. And we're going to give the value of x and y for point A. And that value, we write it as a pair, and we call it 0, 0. Okay. Now this looks very much like a vector, which had components. It looks kind of similar to a vector that had components, two components. So here we're calling the xy component 0 and 0. Now up here at point C, we're going to give this guy a different location because it's all the way up at C. So we're going to call this, we're going to take in the north direction, we're going to say this is 4, and we're going to say we didn't move in the east direction, so we're going to call this 4, 0. That's going to be that point. And now when we get to point B, this is going to be, we're going to call this point 4, 4, because we're going to say, okay, we moved 4 in the north and 4 in the east to get to point B. And then if we look at point D, well, this is a funny point because it's 4 in the east direction, but it's not 4 in the north direction. So in the north direction, we're going to say that that's just 1. And these numbers have units of distance. So we're going to say that's 1 in the north direction, but 4 in the east direction. So now we want to develop equations that describe lines that move between these 2 points. So there's a line that we can find the equation for to move that way, and there's a line that we can find to go that way. And we describe that line in terms of our values x and y. So let's take a look at that process. So this time we're not going to use 2D vectors, but we're going to develop the equation of a line that described motion in this direction and described motion starting from there and going in this direction. So we can use the equation of a line, which in this case is going to be x is equal to something called the slope times y plus x0, which is the value of x when y is equal to 0. And the slope is going to be equal to what we're going to call the change in x over the change in y as you move from your original point to your destination. So for this line, the slope is going to be equal to, so our destination is, the x component of our destination is 4, and the x component of our origination is 0, so we go 4 minus 0. And the y component of our destination is 4, and the y component of our destination is 0 here. So that gives you 4 minus 0. And these are units of distance, so you get a slope equal to 1. Now for the second guy, you get a slope is equal to, so our original point, our destination point, the x is equal to 4, and the original point, x is equal to 1. So you get 4 minus 1, and the original, the destination has 0, and the original has 4. So you have 0 minus 4. And that's going to give us 3. It's going to give us a negative number, 3 over 4. So now we can write the equations for these two lines. So the first one is going to be x is equal to this guy here. So it's 1 times y. And then you look at what is x equal to when y is equal to 0. So they both start off at 0, 0, so it's just 0. Now the second line is this guy. So its slope is minus 3 over 4 times y. And then when y is equal to 0 back here, x is actually equal to 4. So you have to say plus 4. Now that gives us two equations that we call a system of equations that's going to help us investigate this problem. In summary, in this presentation we learned how to derive an equation that describes movement along a line. We developed a system of equations to help us investigate where we might collide with our friend in the sky. So if you want to see the final answer to this problem, please look at part 2 of this presentation. Thank you.